This is the next video in a series on advanced theories of bonding. We just finished talking about sp3 hybridization, and we're moving on to the next type, which is called sp2 hybridization. So you'll know that you need sp2 hybrid orbitals when your central atom has 3 electron groups around it. So let's pick something that has 3 electron groups around the central atom. We're going to pick COF2. And if we draw that structure, it will look like this with the carbon in the middle and a double bond to the oxygen. The only atom in the structure that has more than one bond is carbon, and that's the one we are concerned about the geometry of. So that's the atom we need to hybridize the atomic orbitals for. And carbon is connected to 1, 2, 3 electron groups. And so we need to blend 3 orbitals together in order to make hybrids. So the orbitals we're going to choose belong to the carbon. Carbon has 4 valence orbitals, an s orbital, and 3 p orbitals. But we don't need to blend all 4 of them together. We only need to blend 3 of them together because we only have 3 electron groups to hold. So when we choose which 3 out of the 4, we're always going to choose the s because the s is our favorite orbital with the best possible overlap. And then we'll just choose any other 2 p orbitals. So we're going to blend 1 of the s orbitals and 2 of the p orbitals together, and we'll leave 1 of the p orbitals unblended. We don't need that one. It's not gone. We just don't need to put it in our hybridized machine. So into the hybridized machine they go, and out the other side come 3 sp2 hybrid orbitals. And remember, there should always be the same number going in as there is coming out. So there should be 4 coming out the other side. We need to include that unblended p orbital, which hasn't changed at all. So 3 hybrids and 1 unblended p orbital left over. And in this case, each of these sp2 orbitals is going to be 33% s character and 67% p character. So these are slightly more rich in s character than our sp3 orbitals were in the last video. Okay, so we're going to be making sp2 orbitals out of 1 s and 2 p orbitals mixed together. So then let's look at the shapes of these orbitals. Okay, so our s orbital looks like a circle, and our p orbitals look like 2 balloons tied together. And when we blend them, we're going to get something that looks like a mixture of those 2 shapes. And we know that we are trying to make this sort of a VSEPR structure, a trigonal planar VSEPR structure. And so these hybrid orbitals that we make are going to point towards the 3 vertices of a triangle. So we'll draw them separately first so you can see what they look like with all of the lobes. So we make 3 identically shaped orbitals, 1 pointing towards this corner, 1 pointing towards this corner, and 1 pointing towards this corner. They have 2 lobes, 1 very large and 1 very small, and we really only care about those large lobes. That's where most of the electron density is. So if we draw all of them on top of the same triangle, it would look like this: 3 separate sp2 orbitals, and they sit at the perfect angle to represent the electron geometry trigonal planar, which is the one we would expect this COF2 molecule to have according to experimental evidence and VSEPR theory. So that's good. This is a shape that supports our experimental evidence. So now let's look at the energy. We're hoping to produce 3 new hybrid orbitals with identical energy to use for our 3 electron groups. This is going to be the energy for our carbon atom at the center. So in the last picture, we hybridized all 4 of the atomic orbitals together, but in sp2 hybridization, we only need to blend 3 orbitals together. So I'm going to circle these 3 to blend, and then I'm going to leave 1 p orbital out of the circle that's going to remain unblended. Throw those into the hybridized machine. And out the other side is going to be a series of orbitals that are intermediate in energy between the p energy and the s energy. So our hybrid orbitals are 33% s and 67% p, so they're going to be a little bit less close to the p orbital energy than the last set. So we'll say they're right about here, our 3 sp2 hybrid orbitals. And then remember, we still have 1 2p orbital that we didn't change the shape or energy of, so it's still there. We have our 3 hybrid orbitals, and we have our 1 2p orbital that's the same as it always was in our carbon. And so now that we've made these 3 identically shaped, identical energy hybrid orbitals, we can use them for our sigma bond overlap in order to represent the geometry of this molecule correctly. So we'll put a dot here for carbon, 1 for oxygen, and 1 for each of the fluorines. We can do the carbon first this time. So each of the carbons is going to be contributing an sp2 orbital, just like in this picture we drew on top of the triangle. And then our other terminal orbitals are going to be from the only available half-filled orbitals, which are going to be 2p orbitals. So our oxygen is going to choose a 2p orbital, and the fluorines are going to choose a 2p orbital. And they're going to choose the 2p orbital specifically that has the best overlap along the internuclear axis. Because we need these to form 3 sigma bonds. We have one more kind of hybridization left, and that will be in the next video. That is sp hybridization.